Good morning, ladies and gentlemen. Welcome to PMC pre-training presentation. So as you know, to finish off the vacuum gas oil processing block, we're going to finish it off with the last unit, which is the polynephtha unit. So Pilar will take us through the presentation today. And as usual, we're gonna pause when is required to receive questions or any clarifications that would you like to get. Thanks, Pilar. You can start the presentation now.
Hi, good morning, everybody. I hope you are okay. So we will proceed with the part C of our vacuum gas oil processing pre-training. Remember the vacuum gas oil processing, we have the hydrotreating unit, we have the FCC unit that we saw last week, and today we'll have the polynaphtha unit. These are the three units associated with the vacuum gas oil. We will see today, as usual, the polynaphtha in the Carvala refinery scheme, the purpose, the overall purpose of the unit, the simplified block diagram, and in this unit we have three sections. Okay, we have the alkyphining, we have the oligomerization section, and we have the hydrogenation section. For each of these sections, we will talk about the purpose of this section. We will talk about the feedstock and the product composition, the simplified block diagram, the reactions that take place in the section, the catalyst that we will use it, the main process variable, and we will see the main operating conditions of each of these sections. Okay. So let's start. Where do we have the polynaphtha unit in the Carvala refinery? We have it here. Let's see, first, let's review again the main process. We received two crudes. We received the BASRAP and the MISRIF crude. We have this crude distillation unit. Remember, this is an atmospheric distillation unit. The bottom, we will send it to the vacuum distillation unit. We have this vacuum gas oil. We have pre-treated this vacuum gas oil before the FCC unit. And in this FCC unit, we get our gasoline, okay, that we will send to the gasoline pool, and we will get an unsaturated LPG stream that we will send it to this unit that we will see today to get more gasoline from this stream, okay? Of course, we will get also some medium distillates that we will see during the presentation. But this is where we have our polynaphtha unit. This polynaphtha unit is the licensor, the technology is from Axens. There is a French company, Axens, and the capacity is 11,500 barrels per stream day. Remember, all the capacities that are shown here in this scheme, they are represented as barrel per stream day. So with this unit, we will complete our vacuum gas oil processing module, okay? So we have here our polynaphtha unit. Let's talk about the purpose of the unit. So the light gaseous hydrocarbons produced by catalytic cracking are highly unsaturated. Remember that we saw last week that in the FCC, the fluid catalytic cracking, we don't have hydrogen, so the products that we get from this unit are highly unsaturated and are usually converted into high-octane gasoline components. Mainly, we have two processes where we can improve the quality of these streams. We have the polymerization or the alkylation process. So the idea is to produce more gasoline. In polymerization, the light olefins propylene and butylene are induced to combine or polymerize into molecules of 2 or 3 times their original molecular weight. You will see that sometimes we will call polymerization and sometimes oligomerization, okay? They are not exactly the same, but they are used in the same way in some cases. The alkylation, that is another very used process in the refineries. Reactions also achieves a longer chain molecule by the combination of two smaller molecules, one being an olefin and the other an isoparaffin, usually isobutane, okay? But in our cases, we will use the oligomerization polymerization reaction to produce this high octane gasoline component. So the polynaphtha unit is designed to process an olefinic rich C334 LPG coming from FCC unit to produce a high octane gasoline blending stock. Okay, but just for you to know that in many refineries there are these alkylation units where you will produce also a high octane number product from an olefin combined with an isoparaffin. So we have here our simplified block diagram. The polynaphtha unit is divided into the following 3 sections. We have the alkyphying section, we have the oligomerization section, and we have the hydrogenation section. Let's go and see what happens in each of these sections. The alkyphying section. Here we receive the LPG feed, remember, from the FCC unit. So the LPG feed is pretreated in order to reduce the content of diolefins, water, sulfur, nitrogen, and oxygenate compounds. Why? Because there are contaminants for the next section's catalysts. Okay? For all these catalysts implied in the unit. So we have like to perform a treatment of the feedstock, and this is accomplished in this section. Okay. In all this alkyphying section, we will reduce the content of these components of the feed. In the next section, that is called oligomerization section, the olefinic components of the LPG feed react in presence of a solid catalyst to form the polygasoline and the middle distillate products. The polymerization reactor effluent is then fractionated to recover a polygasoline product, a middle distillate product, and an LPG product. Okay, we will see more in detail of each of these sections, but this is the general overview. So here we produce our gasoline that we will send to the following unit. But of course, we will also produce lighter components and heavier components that we will see to other units. And finally, in the hydrogenation section, we will reduce the olefin content of the polygasoline product in order to meet olefin specification in refinery gasoline pool. So in this unit, you make a step forward and then a little bit back because you cannot send a lot of olefins to the gasoline pool because we have a limitation of olefin content. So we will hydrogenate part of the olefins in this section, okay? So this is more or less the overall simplified block diagram of the section. If you have questions, but we will see each of these sections now in the following slides. So remember, we have three sections: alkyphying, oligomerization, and hydrogenation. So in this alkyphying section, we will treat the feedstock in order to remove the contaminant that will poison the catalyst of this section. Okay? So we will see how we will reduce the contaminants from the feedstock. So the alkyphying section, the purpose is the selective butadiene hydrogenation of an olefinic LPG cut to an acceptable specification for the oligomerization catalyst. That is 100 ppm of butadiene. Because this butadiene is a poison for the oligomerization catalyst, we have to reduce the content of the butadiene in our feedstock. How? We will do it with this selective butadiene hydrogenation. This is the most common butadiene, that is the 1,3-butadiene. Remember that you call it 1,3 because you have a double bond here in the carbon 1 and the double bond here in the carbon 3. And it is diene because you have two double bonds. So this is the 1,3-butadiene in two representation forms. Okay, this is the same. Here you will see the double bonds. Okay, but also this LPG that we will treat to reduce the butadiene. Also, we have some water, sulfur, nitrogen, and oxygenate that we have to remove from this feed. Okay, so as this LPG cut comes from the FCC unit, it is necessary to remove the other compounds that can poison all the catalysts that we will have in this unit. Okay. So these light sulfur compounds, mainly H2S and COS, poisons the alkyphying catalyst, and we will remove in a hot caustic wash drum. The oxygenated nitrogen acetonitrile and traces of caustic we will remove in a water wash column. Arsen is removed in a guard bed, and also water and sulfur are removed in a guard bed at the reactor outlet. We will talk here, reactor is the reactor in this alkyphying section. So we have this purpose in this unit. We will decrease the butadiene content of our feedstock, and also we will remove this other compound from our feedstock. So if you have questions, you can stop me whenever you consider necessary.
So guys, do you have any questions so far? Okay, I don't see any questions, so yeah, you can proceed. Yeah.
Okay, because it's not so easy sometimes to understand why so many steps in this unit, no? But
Yeah.
this first section, it is to hydrogenate this butadiene, okay, because it is a poison for the next section catalyst, And also we have to remove some of these compounds because it also can poison all the catalysts in the unit. Remember that we will have reactors in the alkyphing, in the oligomerization, and in the hydrogenation sections. So this is to remove the contaminants that we can have in our feedstock.
Yeah. Yeah.
So let's see the feedstock and product composition. Always I refer to case one, but remember you have two crudes, so maybe you will have some differences between case one and case two. So this is our feedstock from the FCC unit. Remember that the feedstock to this section is the LPG, the unsaturated LPG from the FCC unit. We have this composition, and this is the main objective of this unit is to reduce the content of the 1,3-butadiene. Here you have the composition of the feedstock, the feed to the alkyphing section, and the product. So the outlet of this section, the alkyphing section, you have here, you reduce the content of the 1,3-butadiene. Okay. We will see now this butadiene will be converted to what we will see in the reactions. But here you have some indication that other compounds will increase the composition. So you have the answer to this question. Also, we will use in this unit the hydrogen. In the hydrogen, remember, in these units, we are using hydrogen from the PSA, so very high purity hydrogen, okay? So this is the feedstock, remember, from the FCC unit. We have this composition, okay? We have a lot of olefins, okay? We have here olefins. We have also isobutene. We have 1-butene. We have this butadiene, okay? That is the contaminant for the oligomerization reactor. We have butanes. We have trans and cis 2-butenes. We have the isopentane. We have also here some olefinic pentane. And we have the paraffins, okay? Pentene and pentane. This is more or less the composition of the feedstock, and this is the product from this section, okay, from the alkyphing section. So this will be the feedstock for the next section, for the oligomerization section. And here the main objective is to decrease this quantity, okay? This 0.15% will go to this quantity of the butadiene in the feedstock. Of course, all this information, you will find it in the process design basis, in this case for unit 9. Okay, the polynaphtha unit is unit 9 in the refinery. So, and this is the document number for this specification. Okay, so let's see. Remember that this alkyphing section, we have two main sections, the polishing and the reaction. Let's start with the polishing section. So the raw LPG comes from the FCC unit. All this section will work in liquid state. So the LPG comes from the FCC unit. LPG is first treated in a hot caustic liquid extractor to react H2S and COS compounds with a 10% caustic solution. First, we will have to increase the temperature. So we will preheat up to 80 degrees C, and then we will go through this to the hot caustic wash drum. Okay, we will use fresh caustic Remember, caustic, uh, it is a sodium hydroxide, and this is a fresh caustic that we will have at 10%. Of course, we will have this spent caustic that we will send offsite for the treatment. And here, in this first step, we will remove H2S and COS, okay, with an appropriate temperature of 80 degrees. Then the LPG without H2S and COS is cooled down to 38 degrees, and then it's treated in a water wash column to remove the oxygenate acetone and the nitrogen compounds and traces of caustic with a water stream of cool medium pressure boiler feed water. So in the next step, we will cool this stream from this hot caustic wash drum, and then we will send it to this water wash column. In this water wash column, the main purpose is to remove oxygenated and nitrogen compounds and traces of this caustic that we have used in the previous step, and how we will introduce this. Remember, this means boiler feed water, and the MP is medium pressure boiler feed water. So in this step, we will remove this, okay, acetone, this acetonitrile compounds, and the traces of caustic. How? We will use water, in this case, and a special water that is the same water that you use to produce steam. You will use it here, so a high quality water. You will use medium pressure boiler feed water, okay, to wash the stream. And we'll also have this spent water that we will send outside the unit for further treatment. So we will have some free water that we will separate in the equalizer. Here we will have some free water removed, and then we will send this stream that we have removed all these compounds in this wash, hot caustic and water wash. Then we will send it to this arsine guard bed, okay, where we will remove this arsine, okay. Also, this is here, it goes to this bed, and then the treated LPG will go to the following section in this alkyphying section, okay? That is the reaction section. So we have here treated our feedstock first, and then we will send it to the reaction section, okay? We have removed the sulfur, we have removed the oxygenate, the nitrogen compounds, the arsine. So now the feed is ready to go to the reaction section, okay? So this is all the description for this polishing unit section. We have removed the H2S and COS with the hot caustic liquid extractor. We have removed the acetone, the acetonitrile, the some traces of caustic with this water wash column. We have separated the free water, and we have removed arsine in this guard bed. Now we will go to the reaction section. Remember, the main purpose, of course, of this section was to selective hydrogenate the butadiene that will take place in the reactor. But first, we had to remove the contaminants for the catalyst. So we will go to the reaction section. Of course, the treated LPG from the previous section, from the polishing section, it is sent to this feed source drum. Then, before entering the reactor, the temperature is adjusted to suit the conditions required at reactor inlet. So we will preheat the feedstock. The hydrogen makeup is mixed in line at the alkyphing reactor inlet. And then we will go to enter the reactor. Okay, the reactor operates in liquid phase. The hydrogenation reactions, remember that we are going to hydrogenate the butadiene, that is a poison for the oligomerization section, the next section in the unit. So we are going to hydrogenate this butadiene. And this reaction, we will have an exothermic reaction. So we will have a temperature rise through the reactor. The selectively hydrogenated LPG is withdrawn from the top of the reactor and is cooled in the reactor effluent coolers. Okay, we will cool our product from the reactor, and then this cold reactor effluent goes through another garbage, okay, to remove water and sulfur. Okay, so when we talk about this garbage, there are adsorbents that we will have here that we will remove the water and sulfur, okay, before sending the stream to the next section, to the oligomerization section. So the idea here in this reaction section of this alkyphing section, remember, is to hydrogen. We will see it out in the chemical reactions, but it's to hydrogenate the butadiene. But we don't want to hydrogenate the other olefins. That's why it's a selective hydrogenation. So we will hydrogenate our butadienes that we will have in the feedstock. This reaction, we need hydrogen, of course. We will mix here. We will send it to the reactor that operates at liquid phase, and then we will cool, and we will send it to this water sulfur adsorbent, okay? And the treated LPG, we will send it to the oligomerization section, okay? So this is more or less the idea of this section. Remember, we have two steps. We have the polishing and the reaction. Okay. Now we will talk about the reactions. Okay. If you have questions about this simplified block diagram before we proceed to see the reactions that take place in this section.
Just a minute, Pilar.
Yes, are they talking about some of the
Yeah,
presentation?
what slides? We have sent the presentation, Mr. Dargham, already. Which slide do you mean? I don't know. Yeah, you can talk to Mr. Ahmed or Mr. Uday. They can pass it to you. Yeah, no problem. Okay. Do you have, guys, any questions about the alkyphining section so far?
Okay.
I don't see any questions.
Okay, maybe at the end, when we see the reactions and all this, we will have okay, an overview again of the section, and we will have
Yeah,
more questions.
sure, sure. Thanks.
So the reactions that take place in this hydrogenation are of two types. Okay, we have the desired reactions, of course, that are the reactions with concord to the purpose of the product. We will have the butadiene hydrogenation. We will hydrogenate into 1-butene and 2-butene. Okay, remember that we will this butadiene, we have two double bonds, then we will hydrogenate only one, and we will keep it, we will have at the outlet an olefin still. We will have a 1-butene and 2-butene, and also we will have this isomerization, okay, of some of this 1-butene will be converted into 2-butene, okay. I have seen that they said in the process in the operating manual that about 60% of the butadiene is converted to butene 1 and 40 to butene 2. Okay. Of course, we'll have reactions that we don't want. And this has, the reactions will result in a loss of valuable component of the feed, such as butene hydrogenation into N-butene or propene hydrogenation into propane. As you have hydrogen, you have the risk to hydrogenate the components that you don't want to hydrogenate, because you have to have these olefins for the next section for the oligomerization. So that's why we call adverse reactions, because we don't want to hydrogenate these compounds, because we will use it in the next section, in the oligomerization section. So these are the desired reactions, is the butadiene hydrogenation, of course, and in some extent also this isomerization, because this 2-butene, it will work better for the oligomerization, okay? That is our next section. So these are the desirable and the adverse reactions. So we have to operate at the right conditions to have these reactions and to avoid these reactions. So this selective hydrogenation of diolefins to olefins proceeds with a high rate and it's exothermic. At these temperatures, the butadiene is hydrogenated into a mixture of butene 1 and butene 2, where the butene 2 that we will have, it is more the trans 2-butene. Remember that you can have the trans and the cis, but in this case, we will have more the trans 2-butene. So this is the reaction. A diolefin plus hydrogen will give you an olefin that we saw, the butene 1 and butene 2. And the isomerization of this butene 1 into butene 2 is also but is less exothermic reaction, and the butene 2 is more reactive than butene 1 in the next section. And this is why this isomerization is required. So this is the isomerization reaction, the butene 1, without any other, it's only an isomerization reaction. It will get transformed into butene 2. It would only change the carbon where you have the double bond, okay? So if you see here at the right is the overall reaction scheme showing the butadiene hydrogenation as well as the consecutive and side reactions can be represented as follows. We will start with this butadiene plus hydrogen. It will produce butene 1 and butene 2. Then we will have in this, you can see here in this arrow here, is represented the isomerization reaction that it will take place also. And that is good. It's good, this reaction, because this butene 2 is more reactive than this butene 1 in the following section, in the oligomerization section. So that's why this reaction is also a good reaction. But here you will have the not desired reactions, because if you keep hydrogenating this butene 1 and butene 2, you have N-butene. And this butane is not good in our unit, because we need olefins for the oligomerization reaction. And remember that all these paraffins, they have very low octane number. So that is not good for our gasoline. So we have to avoid this hydrogenation of this butene 1 and butene 2. And of course, this is also a not desired reaction, that propene will get transformed into propane with the hydrogen, because this is also our olefin that we are going to pass through our oligomerization reaction. So I think that is here well shown all the reactions that take place in this section. Remember, the main objective is to reduce the amount of butadiene, because we have this is a poison for our next catalyst in the oligomerization reaction. How we will reduce it? With a proper catalyst, of course, that will have this selective hydrogenation of these diolefins, the in this compound. So you will react this butadiene with hydrogen, and you will produce butene 1 or butene 2, and then you will have also isomerization of this butene 1 to butene 2, and you will have to avoid these reactions, okay? And this compound, it is better for the oligomerization section. So these are more or less the reactions that take place in the reactor in the alkyphinating section. Remember, we are still in the first section of the polynaphtha unit. We are preparing the feedstock for the oligomerization section. So if you have questions about these reactions.
Yes. Guys, any questions about the alkyphining reaction section? Yes, Mr. Abdul Razzaq.
السلام عليكم حبيبي استاذ احمد
ورحمة الله
حياك الله. العفو استاذ، بس اذا ممكن بخصوص هذا الاندزابل رياكشن اللي يصير، يعني خلينا نسميها الهدرجه الاضافيه،
تمام.
هذه يعني تجنب هذا التفاعل، هل هو فقط يعني عن طريق الاوبريتنج كونديشن مثلا الحراره والضغط فقط، لو اكو مثلا يعني عوامل اخرى تكون يعني تظل هي يعني تحت السيطره، او عوامل اخرى هي لازم تكون مراقبه تاثر على هالشيء هذا؟
Okay, we'll ask Pilar. Pilar, so how you avoid this undesirable normal butane formation? Is it just, the question is it just by adjusting the operating condition?
Yes, operating condition and the hydrogen that you will add to the reaction. No, you have to control very well the hydrogen that you add to inject to the reaction, and with the operating condition.
So basically, you shouldn't have like excess of hydrogen.
Yes. Yeah.
اوكي. استاذ عبد الرزاق، ما اعرف اذا واضح الجواب، يعني هو نفس كلامك.
تمام.
بس
يعني
اضافه الى انه انت الهيدروجين ما يكون عندك به زياده، بحيث اذا انت عندك زياده داخل بالتفاعل، اذا زايد كميه اكسس عن المطلوب اللي ما يمثل
لطيف.
الفكري،
يعني خلينا نسميها كميه الهيدروجين اللي تنضخ هي ضبط على قدر خلينا نسميها انه تكسر البوند الوحده فقط، خلينا نسميها.
وتحول
يعني ماكو اكسس.
تحاول قدر الامكان طبعا، لحد ما تحول بيوتين 1 و 2، هذا حدك يعني.
بس يعني خلينا نسميها اذا لاحظت اكو هدرجه اضافيه للبيوتين تكون اقل للهيدروجين هالشكل.
بالضبط اضافه الى مثل ما قلت الاوبريتنج كونديشن يعني، وكميه الهيدروجين.
لطيف. ممنون عزيزي استاذ، شكرا جزيلا.
Any questions, guys? Comments?
So remember that up to here, these are the desired reactions. Here, we don't want to keep the hydrogenation of these two compounds, and we don't want this propene hydrogenation. Okay.
Okay. Yeah. I don't see more questions. Yeah, you can go.
Okay. So we will. Okay, and this is the use of this catalyst, of course, avoids the complete. That was the previous question. The operating condition, and of course, the catalyst that you will use that will avoid the complete hydrogenation of the olefins. Very specific catalyst for the selective hydrogenation of the olefins. Okay, this is the catalyst that we are going to use. We will see the catalyst now. There is a promoted palladium, an expensive catalyst dispersed on a selected high purity alumina support. This is the shape, not the color, but this is the shape of the catalyst. The feed to the reactor is pretreated to reach the maximum purity level allowed on the catalyst. Of course, remember that we have treated the feed to reactor to reduce as much as possible the impurities, the poisons for the catalyst. Some impurities are considered to be irreversible poisons, such as lead and silicon, whereas other free water, for example, are reversible. Also, you will see in your operating manual that you can have also some in situ regeneration of the catalyst. It is explained how you will proceed with this regeneration of the catalyst. And the volume of the catalyst that we will use in this reactor, in the reactor of the alkyphing section, it is about 25 cubic meter of catalyst in one reactor. So we will see now the process variables that will affect the main process variables of the unit, the hydrogen flow rate. Of course, this parameter is quite important. As we talked previously during the question, if we have a high hydrogen injection, we will lose some of the butenes and propene due to the hydrogenation of these compounds. We will hydrogenate and get the both butane and propane. So we have to have an appropriate hydrogen to hydrocarbon ratio. And of course, if we have too low, we will have not a proper hydrogenation of the butadiene. So we have to have an appropriate hydrogen to hydrocarbon, because if we have too high, we have excess of hydrogenation and we will lose some of our feedstock for the oligomerization section. But if we have too low, we will have a high butadiene content at the outlet. So we have to operate at the right hydrogen to hydrocarbon ratio. This liquid early space velocity, we will see it again, and we will have seen in many of the units we have seen in the training sections. This is the same definition. Okay, it is the liquid feed flow rate at standard conditions divided by the catalyst volume. But in this case, the process are mainly affected by the previous process variable, okay, by this hydrogen to hydrocarbon ratio. Of course, if you want to calculate the residence time, okay, it is the inverse of this liquid early space velocity. Here you calculate it in hours, okay? If you want to calculate the residence time in minutes, you will multiply this volume of catalysts divided by this volume of feed, and you multiply by 60. And you will have the residence time, okay? So it is the inverse of this liquid hourly velocity, and you multiply by 60 to get it in minutes, okay? So this through process variable, this is much more important because it will detect the conversion of this butadiene, and will, if you have a very high hydrogen to hydrocarbon ratio, you will lose some of your valuable feedstock for the next section, that is the oligomerization section. So now we will talk a little bit about the reactor temperature. So the policy, according to the licensor and the operating manual, is to operate at the lowest inlet temperature compatible with a sufficient catalyst activity. That it means with the required butadiene hydrogenation rate. That is our main goal. As catalyst ages, polymers deposit progressive coat the active sites and catalyst activity decreases. And as in many cases, we have to increase the temperature to compensate for this loss of activity. So you will see when we will see the operating conditions that also in this unit we will talk about start of run conditions when you have your fresh catalyst, and with the end of run conditions when you have the deactivation of the catalyst. And you will have to increase the temperature to compensate for this loss of activity in the catalyst. The temperature, the absorption temperature, remember we have absorbers in the unit. So the molecular sieve capacity for a compound increases as the temperature decreases. As the temperature increases, the absorption capacity of the molecular sieves decreases rapidly. The regeneration of the molecular sieve has to perform at high temperature. If you are in the absorption of in the process, we have the absorber, we are working at low temperature during normal operation, but when you regenerate this molecular sieve, you will do it at high temperatures, okay? And the pressure, so for a given concentration of impurities, water, mercaptans, and a given temperature, the molecular sieve absorption increases as the total pressure increases. Higher partial pressure. The regeneration has to perform at pressure as low as possible. So if you, in this case, for these absorbers, it's always the same. If you work at low temperature and high pressure, then when you have the regeneration, you work at the opposite conditions, okay? You will work at high temperature and low pressures. We will see also this when we will see the hydrogen unit with the PSA. We'll see also this same type of adsorption processes. Remember that in this case, we have the adsorber for the sulfur for the water at the outlet of the reactor. We have also the arsine guard bed that is also an absorption process. We have also, remember, when we see the first equipment of this, we have caustic and water washing. So we are going to see now how will impact the rate and the temperature in this washing. If you have questions up to now, up to here, we have seen the hydrogen ratio. We have the liquid outlet space velocity that is not so impact, it is more important this one. We have seen the reactor temperature. We have to work as low as possible, but with the, of course, the appropriate butadiene conversion, and that we will increase the temperature during the time as the catalyst get deactivated. We have some parameters related to the adsorbers. We have the arsine and the sulfur and water absorption. And then we have this parameter related to the rates and temperatures of the caustic and water wash. So remember that we have seen that we will eliminate these compounds, the H2S and the carbonyl sulfide, it's with this caustic wash. And this wash is favored by high temperature, more or less 70 to 80 degrees C. In any case, it is forbidden to increase this temperature because you can have some caustic cracking. And in the case of a water wash, remember that we use this water wash for the removal of oxygen compounds, mainly acetone, and also for the nitrogen compounds. So the performance of this water wash are increased at low temperature. That's why remember that we heat it in this washing section. What about the concentration? Remember, here when we talk about caustic wash, we are talking about using this 10% sodium hydroxide solution, okay? And we have to keep it at 10%. If we have a higher concentration, we can have the risk of a stable emulsion for the current design. And so we will have worse extraction of our sulfur compounds. And if we have a lower one, we will reduce the sulfur compound extractions. So we have to keep it at this concentration because we cannot have, we should not have it higher or lower, okay? We have to keep it the solution at this, the caustic solution at this concentration, at 10% concentration. This is, of course, this washing solvent rate can be increases if we have higher impurities in the feed, but the rates, okay? Washing solvent rate can be increased if we have more impurities in the feed. Oops. Okay. So these are more or less the process variables for this alkyl section. Remember that is the first section before we go to the oligomerization section. In this section, we will remove some contaminants from the feed and we will have a reaction. What reaction we will have? We will have the selective hydrogenation of diolefins, mainly the 1,3-butadiene. It will be converted to butene 1 and butene 2. So now we will see some of the operating conditions, but if you have questions before we move to the next section and to the operating condition of this alkyl section.
Guys, do you have any questions? Because we're going to move to a different section here. Okay, don't see any questions. So.
Okay.
Yeah. Yeah, you can proceed, yeah.
Can you hear me now?
Yes, I do know.
Okay.
But
what happened with the connection?
Slide disappeared, yeah.
Okay. So you see the slides now?
No.
No?
No, you need to share it again, I think.
Well, guys, I have lost the operating conditions for this first section. You can see here, of course, we are operating upflow in the reactor. We have this liquid outlet space velocity of 3. Oh, yeah. Okay. That's the point. Okay. Of 3. Here I have put the calculation. Okay. We have this flow rate of 76.2 km per hour. And we have this catalyst volume. So we have this liquid outlet space velocity of 3. We have the reactor inlet temperature. We have at the start of run conditions, we have 250. And during the time, we get up to 83 at the end of run conditions. At the reactor outlet, we will have 60. And at the end of run condition, 97. And we are working at this temperature, at this pressure, okay, more or less. We have at the inlet of the reactor 30 kilograms per square centimeter gauge, and at the outlet of the reactor 28.3. This hydrogen makeup flow rate, we have at the start of run condition 14, and you will see that in this case also not only the temperature, but we have to increase also the hydrogen during the time as the catalyst loses activity to push the reaction. Okay, you have also to increase the hydrogen makeup flow rate from 14 at the start of run conditions to 38 at the end of run conditions. Okay. So let me see if I can. Okay, this was the maybe. I don't know why I don't have these files here. No. Okay. When we come back from the break, I will show you the PFD of this unit. Okay, just to explain you more or less these operating conditions on the PFD.
Okay, yeah, no problem. So we'll take a break, maybe 25 minutes. So we
Okay.
In Iraq time, I think it's 11:30, and now it's 5 past.
Okay, perfect.
So شباب خذوا 20 دقيقة بريك ونرجع إن شاء الله.
we have finished the first section of the polynaphtha unit, that is the alkyphying section. Okay, so here you will see the process flow diagram for the reactor in the alkyphying section. So you see here the hydrogen coming in. Okay, here in this stream, the hydrogen is coming in. We have here the flow at the start of run condition. Okay. Here we have the 14 kilograms are a start of run conditions. And then we have here the reactor, okay? That is the 09 R101 with the catalyst volume that is 25.4. Here you have this is the reactor, okay? And here you have the catalyst. So you enter the hydrogen in this sense, and you mix with the feedstock, okay? That comes here at the bottom. This is the quantity of the feed. This is the quantity. There is the 76.2. Remember that we used to calculate the liquid or space velocity. You mix in this mixer with the hydrogen and you go into the reactor. Okay. Then with these conditions, 50 degrees C at the start of run condition and 83 degrees C at the end of run condition. At the outlet of the reactor, you have this other condition at the top. Okay, you will see it. There you have 60 and 99 for the end of run. And then the outlet of the reactor at the top of the reactor will go to these absorbers that are the final absorber for the water and sulfur removal before going to the oligomerization section. You will see in these PFDs, yeah, you will have also some streams, yeah, at the top. For example, this that I am marking now in red. This is it says normally no flow. There are lines that you will use when you will regenerate the catalyst. Okay, so that's why in normal operation you will see normal no flow for these streams. Okay, also here in these dryers you have two dryers. Okay, A and B. So you will have one dryer in operation. Okay, and the other dry will be in regeneration. Okay, the B in this case will be in regeneration. And in this case, remember that the importance to have the right amount of hydrogen in the reactor to avoid further hydrogenation of the components that we are going to use in the following section. Here you have an online analyzer. You see at the outlet of the reactor. Okay, that is it will tell you how much 1,3-butadiene you will have at the outlet of the reactor, and it will send the signal to the calculation of the hydrogen that you will require to add to the reactor. Okay. Of course, remember also that I told you that during the startup aroma condition, you add more or less 14 kilograms per hour of hydrogen. At the end of run, you will have to add more hydrogen. The other quantity of hydrogen, you will add it directly to the reactor at the end of run conditions. And it is shown here at the bottom of the reactor that you will have also an inlet of hydrogen, okay? That is the stream 115. They have put this other way to add hydrogen because with this quantity of 14 kilograms per hour, it's more related with the solubility of the hydrogen in the feedstock. So It will have a quantity of hydrogen going to the mixer and the rest of quantity of hydrogen going directly to special distributors in the reactor. Well, this is more or less this reaction section of this first section of the polynaphtha unit. Then we will continue with the presentation. If you don't have questions, please.
Thanks, Pilar. Guys, do you have any questions on the PFD? Okay, don't see any questions. Yeah, you can go ahead. Yeah, thanks.
So, so let's move now to the following section. That is the oligomerization section. So what is the purpose of this section? The purpose of the oligomerization section of the polynaphtha unit is the oligomerization of these olefins, propylene, isobutene, and normal butenes, leading to gasoline and methyl distillate cuts. What is the difference when we talk an oligomer and a polymer? We will see. In chemistry, an oligomer is a molecule that consists of a few similar or identical repeating units, which could be derived actually or conceptually from copies of a smaller molecule. It's monomer that we call it, okay? The name is composed from the Greek elements oligo, a few, and mer, parts, okay? So an oligomer, it is a molecule that you will repeat few times the same molecule. And the polymer that we use to say it is a compound with large number of units, okay? Possible thousands or millions of the same unit repeated. So if you see the here at the right, this drawing, here, this molecule, we call it monomer. We go through the polymerization reaction, and we get a polymer. This polymer can have thousands of this monomer. But in the oligomer, we have 2, 3, 4 only molecules in the chain. Okay, that is the main difference, because poly in Greek is many, and oli is a few. So the oligomer will have few molecules than the polymer. Okay, that is the main difference, but it's used sometimes the same polymer and oligomer. It doesn't matter if you have few or many. Okay, so oligomerization is a chemical process that converts monomers to macromolecular complexes through a finite degree of polymerization. Okay, you stop it, the polymerization at some degree. You don't go to the complete polymerization of the monomer. Okay, so that's the phenomena that we are going to see in this section, the oligomerization. Okay, and this is the difference between a polymer and an oligomer. Okay, the poly is many of these monomers, and the oligomer few monomers that we have together. Okay, so the purpose of the unit is the oligomerization of the propylene, isobutene, and normal butene. Okay, to produce gasoline, and we will produce also some methyl distillate. Okay, and we have here the definition and the difference between an oligomer and a polymer. Okay, so what is our feedstock for this section? Is the product from the previous section. This is the product from the alkyphying section. Remember, we have this more or less this composition. We have hydrogen, ethane, propane. We have propene, isobutane, butane, 1-butene, tris-2-butene, C2-butene. So at the outlet of this Wait, let me, okay, I was telling, okay, so this is our feedstock for alkyphine, okay? We have two tables. This will continue in this table, okay? We have our 1,3-butadiene, we have olefins and some paraffins, okay? Some C5 plus olefins and C5 plus paraffins. At the outlet of this oligomerization section, let's see this. We have almost no C5 plus olefins, 0.334. But at the outlet of this oligomerization section, we have 92% of olefins at the outlet of the composition, okay? And you will see how this will transform all these olefins in C5 plus olefins in this oligomerization reaction, okay? That is the importance of this reaction, okay? To transform these smaller olefins in bigger olefins, okay? Of course, this data you will have in the process design basis of the unit. So the idea is that the feedstock from the alkyphining unit will go through the oligomerization unit to have this more production of the C5 plus olefins, okay? From these smaller olefins. Let's see how we will get this in this section. So the reaction involved in the polynaphtha process is the deep oligomerization of the olefinic C3-C4 cuts, okay? C3 and C4 olefins react on the oligomerization catalyst to form dimers. So you have a C3 olefin plus another C3 olefins and will react and produce a C6. If you have one C4 and another 3,4, will produce a C8. If you have a C3 plus 3,4, you will produce a C7. Okay, of course, this reaction is this is a dimer because you have two, okay, but it can continue and you can have trimers, okay. If you continue to react one C3 olefin plus one C8, we will produce C11. If you react C4 plus C8, C12, and so on, okay? So this is the basis of this oligomerization section. You react, you have reaction between olefins to have this type of dimers or trimers, okay, products. Okay, so these are more or less the reactions that will take place in the unit, okay? Remember that we have, if we go to back, we have these olefins, okay? All the olefins in this, in the feedstock, okay? So it will be combined, it will react, and it will form these olefins here at the outlet of this section. We have these reactions, okay. And of course, for these reactions to happen, we need a very specific catalyst. Okay, this reaction takes place with a catalyst. The catalyst that we will use is a silica alumina type catalyst. This is the shape of the catalyst that we will use in this section. The specific high selectivity of the promoted catalyst results in long operation cycles due to very low gums deposit on the active surface. We'll see later what is gum. We will see the definition. The catalyst mechanical strength is very high, being unaffected by accidental presence of water and other impurities, accidental, not continuous. In situ or ex situ regeneration of the catalyst can be used to restore the activity without altering its mechanical properties. And we will have here 3 reactors in this oligomerization section and the reaction. We have the first reactor that we will have, we will see that we have 2 reactors with each one with this quantity of catalyst. We have a second reactor and a third reactor with 96.7 cubic meter of catalyst each one. So this is a silica aluminum type catalyst. It has a high selectivity, so it will produce what you want to produce, and the mechanical strength is very high of this catalyst. Of course, we'll have to take care of the catalyst. We have to avoid any contamination, and we have remember that we have treated the feedstock. We have reduced the butadiene and all the contaminants to protect this catalyst. I don't know if you have questions so far, or we can proceed with the process flow description.
Let's see, do we have questions, guys, so far on the oligomerization section? Okay. We've got one question in the chat. Let's see, the catalyst volume of first reactor is much lower than the other reactors. Why is that? Because it's exothermic reaction? Question. To control
Yes.
temperature, or we want reaction in first reactor less active because of fresh feed. So the question is why there is a variation in the volume in different reactors. Yeah.
We have 2 reactors, 2 first reactors, okay? Each one with this quantity, and we will see later also, okay? They will put this first reactor, we have an spare of this first reactor, okay? It's the only one that has spare, because the second reactor is only one, the third reactor is only one. The first one is like protecting the activity of the other ones, okay? It's like a sacrifice, they will sacrifice for the other reactors. So you will have the possibility to regenerate the first reactor while you are operating the spare of this first reactor, okay? But we will see later that we'll see also more about why we have 2 first reactors, okay? Because of course it will be the first reactor that will deactivate earlier than the other ones. But they have designed it that you can regenerate this first reactor catalyst only, okay? While in operation during normal operation, okay? But we will see it now in the process description. So let's see first the okay. Okay. Let's see first the reaction section. Remember that also in this oligomerization section we have 2 steps: the reaction and then the separation. So the treated LPG from the previous section, remember the alkyphying section, is mixed with a recycle coming from the debutanizing, that is a column that we will see later, and this recycle is used to dilute the olefins content of the feed. Okay, so we have our treated LPG from the previous section, that is the alkyphying section. We will have here this recycle from the column, and we will go to this feed source drum. The feed is heated and sent to the first polymerization reactor. We have here some heated to heat up this LPG from the alkyphying section. Okay, the polymerization reactors are operated in outflow mode. A spare reactor of the first polymerization reactor is provided in order to avoid unit shutdown during catalyst reactivation and to maximize second reactor catalyst cycle. Okay, so that's why we have two reactor for the first polymerization reactor, and that's why I suppose they have split the catalyst volume in two in this case for this first reactor. Okay, so we will see also clear when we will see the PFD. Here you see only one, but in the process flow diagram, we will see that we have two of this one, okay? The same size, but two first reactors. The reactor effluents are cooled down to the required temperature using intercoolers. Okay, so from the first reactor, you will cool the outlet of this reactor and you go to the second reactor. Then you will cool it and you will go to the third reactor. Okay, and then you will go to the debutanizer column. Okay, the pressure will be increased and we will go to the distillation unit. Decrease to fit the distillation section, sorry. Decrease to fit the distillation section. So we have here the reactors where the reaction that we have seen, the oligomerization reactor reactions, remember, it will take place. So we have now to separate the different products and the different codes that we will get from these reactors. For this, we will move to the distillation section. So the polymerization reaction section effluents are sent to the debutanizer in which the 3,3-C4 cut is separated from the oligomers produced by the reaction. Okay. Remember that we have also some 3 and C4 that didn't react during the oligomerization, so we will separate in this debutanizer column. The debutanizer overhead is condensed and cooled, and part of this liquid, remember that we have some recycle, so it is where the recycle is coming from the top of the debutanizer. We will mix with the feed to the reactors, okay? It is to control the olefins content and of course the temperature in the reactors, okay? So part of the liquid returns to the debutanizer as reflux and part is recycled to the polymerization feed source drum, and the rest is sent to the LPG production section, that is another unit in the refinery that we will see in other sections. Okay, so we will use part as a reflux coming back to the debutanizer. We will see part as a recycle that will be mixed with the feedstock, and the rest we will send to the LPG production section. The bottom of the debutanizer we will send to the splitter. We have here our main products, where we will have heavier and lighter, so we'll have to go to a splitter. In the splitter, the gasoline and middle distillates produced by the oligomerization reaction are separated. So we'll have here our polygasoline, that is our product from this oligomerization section, that we will send to the following section of the polynaphtha unit. And we'll have this splitter, it operated at some vacuum conditions. So we have a vacuum system that it will keep the vacuum in this unit. We will use some ejectors with steam. We have, of course, some water produced, and we have some lighter stream that will have to this unit, but we will use it as fuel in this unit for the heater that we have in the naphtha hydrotreating unit. Okay, that's the system that we have to for the splitter, okay, to operate at vacuum condition. And the bottom product of the splitter we will send to the diesel hydrotreating unit, okay? Remember that we will have heavier compounds, that it will be not adequate for the gasoline pool, so we will send it to the diesel hydrotreating unit. So the idea in this section is first to separate the C3, C4 stream, and then to split the bottom of the debutanizer into our polygasoline, that is our product, and we'll have also some middle distillate. We'll have some lighter components that we will use in this unit, but as a fuel for the furnace that we will have in this naphtha hydrotreating unit. So this is more or less the simplified block description for the oligomerization section. Remember, we have two separate two sections, the reaction and the distillation. In the reactions, we have 3 reactors. We have, for the first reactor, we have an spare, and we will produce our oligomer. We will see the process variables that that are important in this unit. And in this distillation unit, we'll have the separation of our product from the rest of the lighter and the heavier components. Okay, so if you have some questions, or we can go to the process variables for the oligomerization section.
Guys, any questions? No questions, okay.
Okay. So the main process variables for this oligomerization section, we have the C3, C4 fresh feed flow rate, the recycle ratio, remember, from the butanizer, the liquid early space velocity and residence time, and the temperature. So let's start with the 3C, C4 fresh feed flow rate. So both feed flow rate and its content of the propenes and butenes are important because they determine the product rate. Okay, remember that we will react this with this to make our oligomers. The recycle ratio, that is, remember, from the debutanizer at the top, we will get a C3, C4 that is essentially paraffinic, where remember what it means. Paraffinic saturated alkanes is used to dilute the highly reactive unsaturated C3, C4 compounds containing the free feed coming from the alkyphinin unit, okay? It is used to dilute these unsaturated compounds. And the purpose of this dilution is to absorb the heat released by the oligomerization reactions, to limit the temperature gradient across the reactors, okay? So it is a question to limit the temperature in the reactions, the reason why we use this recycled stream from the butanizers, okay? Here again, we talk about the liquid outlet space velocity and residence time. So at high liquid space outlet space velocity, what it means that we have a high flow rate, the residence times in the reactor will be lower. This will lead to a decrease of the olefins conversion. Moreover, the formation of dimers and trimers will be selectively increased, and the production of heavier oligomers will decrease. So the production of gasoline will increase, whereas the production of middle distillate will decrease. I have here put also the calculation of the residence time. And if we have low our liquid outlet space velocity, it means that we have low flow rate. The residence time in the reactor will be more important. This will lead to a more important conversion of the olefins, and the formation of heavy oligomers will be facilitated. So the production of gasoline will decrease and the production distillate will increase. So the opposite of this one. So you have to work at the design liquid early space velocity, okay, to have the proper distribution between gasoline and middle distillate. Here you have the calculation for the liquid early space velocity. We have this liquid flow rate entering the oligomerization section. This calculated also adding the recycle. Remember that we have the recycle from the top of the debutanizer, this paraffinic stream. So we have this total amount entering the reactor, and we have this total catalyst volume, okay, for the all the reactors. So we have here calculated the liquid hourly space velocity and residence time. Also, an important parameter of the process of this section is the temperature. We see here that as the catalyst ages, the polymer deposit progressively coat the catalyst at deep surface and catalyst activity decreases. So, as in other units that we have seen, we have to increase the temperature to compensate for the loss of inactivity. These reactions is highly exothermic. So butene conversion is favored at lower temperatures. Higher temperatures, however, favor conversion rates. Also, they compromise between kinetic and thermodynamic in the reactions, okay? So you have a favor, but a lower temperature because it's exothermic, but higher temperatures will increase the conversion rates. The higher temperatures favor the formation of higher oligomers. Very high temperatures induce polymer formation and thermal cracking reactions, and then you will have coke deposits that, of course, are detrimental to catalyst life. So the policy we have seen also for the alkyphinin section is to operate at the lowest inlet temperature compatible with the sufficient initial catalyst activity and to take advantage of the liquid recycle to limit the temperature rise. Remember the recycle ratio, it is quite important to limit this temperature rise in the reactors. So these are more or less the process variables in this section. Remember the feed, of course, the content of the olefins on the feed that will give you the product that we will get from this oligomerization section. The recycle ratio to limit the temperature increase in the reactor. We have, of course, to have the appropriate liquid early space velocity and residence and the associated residence time to have the quality of the product between the gasoline and the middle distillate that we get from the section. And we have the temperature that is quite important because this is a highly exothermic reaction. So we have to work at the appropriate temperature in the reactors. So if we see the operating conditions, always related to case one, okay, we have here the main operating conditions, okay. You can have here the liquid hourly space velocity that we have seen how to calculate it, that is 0.8. Let me see, because I have repeated here again. Okay, I have here 0.8. We have here the reactor inlet temperature at the start of run conditions for the first reactor. And you have here the outlet temperature. So you see the increase of temperature due to the reactions. They are exothermic reactions. And then you will see also here the temperature of the first reactor at the end of run condition. Okay, remember start of run when you have fresh catalyst, and the end of run when you are close to the activation of the catalyst. You have at the end of run conditions at the first reactor, you have this temperature, and at the outlet this temperature. Where we are working here at high pressure. Remember, we want to keep the liquid phase in all these reactions. And you will have here the conditions for the other reactors. You will see that more or less, of course, you have the intercooling between reactors. You have more or less the same temperature conditions, okay? 120 for the start of run, and 170 and the outlet conditions. And you will see, of course, you have here the first reactor inlet pressure. You have some pressure drop across the reactors, okay? So these are more or less the operating conditions for this oligomerization section. So please ask if you have some questions. I will try to show you, yes, the PFD for this section. But if you have some questions.
Yeah, we've got Mr. Amir.
Yes.
Yes, but I have one question.
Hi.
That's why the first reaction have a lower volume of catalyst because we need to keep the temperature
Yes, control
at
the
the
temperature.
same.
Mm-hmm.
So because the reaction is exothermic.
Yes, and then you have, of course, the first reactor will see more more product for more feedstock, active feedstock, and that's why they have split the first reactor into two reactors that we can see it here in this PFD. You have here the two reactors, okay? For the first reactor, the only one that you have two reactors, okay? You have, you can regenerate one reactor while keeping the operation of the plant, okay? That's why the importance of this spare reactor, if only for the first reactor, okay? And you have split the total volume in two reactors, more or less the same quantity of the other reactors, but into two reactors. Yes.
It's work as a lead and lag or what?
Yes, yes, and it will to preserve these reactors, you will sacrifice more the first reactor, and you can have longer life of these two other catalysts in the rest of the reactors.
Okay, thank you.
Yes. So you have here the inlet to the section. You have here the inlet, okay, the treated LPG from the alkyphine with this flow rates, okay? You have here the blue stream, that is the recycle, okay? As you can see, it is a high flow rate, okay, of recycle. Yeah, you have to keep to control the temperatures rise in the reactor. And then you will go to this drum, and then you will go to the different to the reactors, okay? So this is more or less the PFD for this unit, no? you have the 3 reactors, and then the outlet of the reactor 3, it will go to this heat exchanger, and then you will get the appropriate temperatures to go to the debutanizer column. Okay. So this is remember the important things, of course, to keep the appropriate temperature, to keep the recycle with the feedstock. Okay, you will combine the feedstock with the recycle, that is a paraffinic stream coming from the debutanizer. Okay.
Pilar, we've got just one question.
Yes,
If
yes,
I
please.
understand it well, it says why the middle no, I don't.
السلام عليكم أستاذ.
ورحمة الله على راسك.
أستاذ، هو على سلايد 29 يعني دا أقول ليش انخفض إنتاج الميدل ديستيليت عندما يكون معدل الجريان الهاي يعني الليفل مالته يكون هاي فلو.
Question, Pilar, if you go back to slide 29, says if we still have like high volumetric rate, why the middle distillate rate being reduced? I think that's what the question is. 29. Yeah, so if you go to 29, middle distillate. Okay, so the last paragraph says, okay, no, the first paragraph says dimers and trimers will be selectively increased and the production of heavier oligomers will decrease. So the production of gasoline will increase, whereas the production of middle distillates will decrease.
So if you remember that in the splitter, after the debutanizer, you will separate the lighter oligomers from the heavier oligomers. The lighter oligomers will be sent it to the hydrogenation, and the bottom, it will be the heavier oligomers that will send it to the diesel hydrotreating unit. If you have less heavier oligomers, you have less quantity of this middle distillate. These middle distillates are the bottom of the splitter that we will send it to the diesel hydrotreating unit. Okay.
Okay, so I think it's just the terminology.
Yes, maybe. Yes, it's a little bit confusing.
So let me explain. ست دعاء
نعم
الفكرة
أستاذ.
البوتوم بالسبلتر عندنا هيفي ولايت اوليجومرز صح؟
نعم.
البوتوم اللي مسميها هيفي اوليجومرز هي اللي تروح للديزل هيدروتريتر. فالديزل لانه ديزل فهو يعتبر ميدل ديستيلتس.
لا أستاذ، مو هذا سؤالي. سؤالي إنه ليش يكون إنتاج الميدل ديستيليت من يكون عندنا معدل الجريان الحجمي هاي فلو ريت، ليش يكون ديجريز؟
مو انت ديكريز، مو انت على من انت شنو الافضل؟ الظروف الفاريبلز البروسيس فاريبلز واحده منهن هي ال اتش اس في. اذا
نعم.
زاد هذا افضل في انتاج شنو؟ البوليغازولين، صحيح؟
نعم.
فمن كل ما تزيد ال اتش اس في كل ما يزيد انتاج الغازولين اللي هو المطلوب من الوحده. هدف الوحده هو انتاج البوليغازولين، صحيح؟
نعم صح.
انتاج البوليغازولين كل ما يزيد يقل منه عندك الهيفي اوليجومرز اللي هو من هو الهيفي اوليجومرز اللي هو الديزل. فان احنا غرض الوحده مو انتاج الديزل، غرض الوحده انتاج الغازولين.
نعم.
فبالنتيجه كل ما ال اتش اس في اعلى كل ما انتاج الغازولين اعلى اللي هو المطلوب هذا.
اللي هو البيربس.
اذا زاد ال اتش اس في يقل الديزل، اذا قل ال اتش اس في راح يزيد الديزل اللي هو غير مطلوب يعني.
اوكي استاذ، اوكي تسلم.
Okay, any more questions? I don't see any more questions. Okay, you can proceed.
Okay, so we have seen the oligomerization section. We have seen that we have produced our olefins we have increased the olefins content, the C5 plus olefin content, but now we have to go back and we have to hydrogenate some of these olefins because we have some limitations in the olefins content in our gasoline pool, okay? So let's see the purpose of the unit, of this section of the unit, that is the hydrogenation section. So in gasoline, olefins contribute to octane number, which is good, it's beneficial. However, because they tend to form harmful deposits inside of engines, there are typically limits set on the total olefin content. Refinery streams containing high percentage of olefins have a tendency to polymerize and form gums because the double bonds are reactive and the compounds are more easily oxidized and polymerized to form gums, okay? So what is a gum? It's a sticky substance that forms by the oxidation of gasoline, especially those stored over a long period of time. These are very harmful for the car engines, especially for the fuel injection ports. That's why we don't want gums formation, and the gums are formed by the olefins presence. So the purpose of this hydrogenation section is to reduce the olefin content of the polygasoline product in order to meet olefins specification in the refinery gasoline pool. The polygasoline hydrogenation section consists in a partial hydrogenation reaction that is about 50%. Okay, so we will see now more about this section in these following slides. Okay, we see here the purpose of this hydrogenation section. As we have seen, is to have this hydrogenation, partial hydrogenation, that is by design a 50% hydrogenation of the olefin content. So you can see that this is the reason why do we have to have this hydrogenation reaction is because the gum formation, okay? And the olefins is the main precursor for the gum formation. And we have a specification for the gasoline pool that you cannot have more than 18% volume of olefin in the gasoline pool, okay? So let's see now the feedstock and the product composition. So that's what I told you before, that is unit is that, okay, you make a product and then like you go back, you you hydrogenate part of the olefins that you have produced, but this is the reason. So let's see now some of the specification of the characteristic of our feedstock and the product. This feedstock to the hydrogenation section, it is from the oligomerization section. Remember the previous section that we had almost 92% of olefins, and we have this paraffins content. And then the product that we will get from this hydrogenation section, it will be this. As you can see, and we can see this product to the gasoline pool. As you can see, we have decreased the olefins content. It is in this stream from 92 by half, almost, to 46.6, okay? So this is, and of course, we have converted to paraffins. The olefins that we will hydrogenate, we will convert it to paraffins in the C5 plus stream. Then, of course, in this, as you can see in the name of the section, is a hydrogenation section, and then we will need hydrogen to perform these reactions. where we will get this hydrogen from the PSA, because we need high purity hydrogen. So we will get this hydrogen from the PSA. That, remember, there is another unit in the refinery for the hydrogen production and purification. So we have a high purity hydrogen for this section. But this is important to understand that we are decreasing the olefins content from 92 to 46 in the stream, okay? So let's see how we will do these reductions in the olefins content. Of course, all the data comes from the design basis of the unit. So in this case, we will see we'll have a reaction section, of course. We'll have the hydrogen makeup is mixed with the polygasoline coming from the oligomerization section. And with the recycle stream, we will see this recycle. The static mixer is installed to ensure a good mixing between hydrocarbons and hydrogen. Okay, we will mix here the hydrogen with the feedstock and this recycle. And then we go to the reactor, to the hydrogenation reactor. The effluents, the outlet of the reactor, flows to the separator drum. Vapor from the separator drum enters these condensers. Vapor from this condensing system will send to the fuel gas system. Remember that in the refinery we have a fuel gas network, so this will be sent to this fuel gas system. And the liquid that will be condensed in this system will be returned to this separator drum. One part of the liquid of the drum is returned to the to the hydrogenation reactor to dilute the oligomer feed and to reduce the exothermicity of the reaction. Remember the recycle also that we saw during the oligomerization reaction from the debutanizer. What is the idea also here? We use part of this liquid as recycle. The other part is sent to the polygasoline stabilizer, okay? So that we will see in the next slide. So the idea here is that you have your feed to this hydrogenation section. Of course, is the product from the previous section, that is the oligomerization section. Then you will mix with the hydrogen makeup and also with this recycle coming from the separator drum. You will mix and then you will go to the reactor where you will have your hydrogenation reactions. Then you will go to this separator, you have some lighter components that you will send to the fuel system, and you will have your product that you will send to the next section. And this same product, part of the product, we will recycle to dilute this stream. So let's go to the stabilizer section. So the hydrogenated polygasoline from the previous slide, remember? It is sent to this stabilizer. Then in this stabilizer, of course, you have an overhead vapor phase. You will cool this stream from the top of the stabilizer, and you will go to this separator drum. The lighter components will be sent to this fuel gas system, and part, of course, will be recycled. The liquid hydrocarbon from this reflux drum, it is the reflux that goes back to the stabilizer. Okay. And the bottom product of the stabilizer is our product, okay? Before we send this gasoline to the storage, we have to cool down this stream from the bottom of the stabilizer. Also, when we will see, we have an online session about blending and product, we will see more or less the different streams that we will mix, we will blend in the gasoline pool. And one is, of course, this polygasoline that we will use in our gasoline pool. In this case, also this antipolymerization agent, it is injected here. Remember, these streams containing polymers, oligomers, will tend to form gums if you store for longer period of time. So you will add some anti-polymerization agent here before sending it to the storage. So this is the stabilizer section of this hydrogenation section of the polynaphtha unit. So as you can see, the idea of this section, you hydrogenate part of the olefins content that you have from the oligomerization section. This is due to meet the specifications of the olefins content in the gasoline. And then you will, as design basis, you will hydrogenate 50% of the olefins content of in the feed. But we'll see when we will see also the operating parameters that also the unit is designed for 75% hydrogenation and 25% hydrogenation. Okay, I suppose that is depending on the gasoline pool, but the design is 50%, the normal design basis. Okay. I don't know if you have questions about these simplified block descriptions, because
So,
now...
can you repeat what you said about the 70% and the 20%?
Yes, when I was reading the operating manual and the operating variables, they talk also that the unit can operate to have a 25% hydrogenation and also a 75% hydrogenation. So the only thing that you have to change is the hydrogen rate that you add to the unit, okay? But I suppose that it will depend also in the gasoline pool and if you can have more olefins or less olefins in this stream that is part of this gasoline pool, no?
Yeah, but I think this is, I'm not sure whether this going to be done manually or auto. I think it's up to the operator maybe to decide.
And it's up to the operator, yeah, yes. If you decide to go to less or to go to more hydrogenation, yes.
Yeah, so just for how many slides we've got left, 6 or more?
I don't know.
6
Yes,
slides, yeah.
yes, the process variables, the reactions of the process variables.
Take like 10 minutes break before we finish off, because maybe I think the time it's been more than 1 hour, I guess.
Do you want to a break now? No?
Yeah, short break, 10 minutes
Okay.
maybe.
Okay, so let's see now in 10 minutes. Okay.
شباب تاخذون 10 دقائق بريك لو شنو رايكم؟ اي لا ماكو جواب؟
ابو يوسف انا دخلت متاخر، شنو اخذت استراحات طويله لو لا؟
احنا اخذنا طويله بس بقى اصور يعني شويه اللي هي المحاضره.
لود صار؟ هاي اوكي ماشي 10 دقائق 10 دقائق. هسه ما ونوصل الا ثلث غير؟
اوكي 10 minutes بيلار just
10 minutes break يس اوكي.
ثانكس بيلار.
اوكي.
شكرا
يوسف. استاذ احمد.
هاني.
نشوف العدد ترى عندك 40 هسه بالمصفى و40 طلعوا يعني ب 12 يلا يوصلون. فعمليا عندك 40 نقص.
دائما هو 40 الحضور، هو مو
هذا 40 نقص صار، يعني كان 25 هسه صار 40 وجبه الاخ ودينا، يعني
هو
صار 40 تقريبا.
يعني احنا الحضور ناقص 3 او ناقص 4، فالحضور 35.
ايه 35 زائد 40 فد 75 يعني تقريبا نفس الرقم.
لا بس هم
هاي راح يكون واحد ناخذها بالاعتبار يعني، لانه منه هيك، لان صار عندك دائما 40 بالدوره يوميا.
زين. بس
هسه الوجبه الثالثه بدت يعني 25 كانوا وزيدنا 14
شو وقت
صار 39.
شو وقت يحضرون المحاضره؟
هذول مثلا باكر اذا مثلا محاضره اي الاثنين او الاربعاء
لا هسه
يتقسمون عليهن، يعني حتى نفتح لهم الموضوع، مو مشكله جروب اي جروب بي.
هذا مو
اللي ما يقدر مثلا بالاثنين يحضرها بالاربعاء، بس هو عمليا يوميا عندك نقص 40 نص العدد، اضافه للغياب اذا صار فتصير بالثلاثينات الاعداد من هيك. فهاي ما ادري شلون يعني تاخذها انت بنظر الاعتبار بالامور.
ناقش فيها ورد
ان شاء الله ماشي ماشي. خذ راحتك.
اوكي.
Okay, so we have seen in the halogenation section that we have the two sections in the section. We have the reactor and the stabilizer. So we will see now the reactions that take place. So the main reactions, we have the olefins that will react with hydrogen to produce a paraffin. And if we have aromatics, we'll have aromatic plus hydrogen will produce a cycloparaffin. Of course, we have also side reactions. Let's read it here first, what it say about the main reactions. The halogenation is an equilibrium reaction which results in the reduction of the total number of moles. As a result, the most favorable operating conditions include high pressure. It's also one thing that we have discussed in all these sessions, that if you have 2 moles here, 1 mole of olefin and 1 mole of hydrogen, and you will produce 1 mole of paraffins, so you will have you will favor the reactions if you have high pressure, okay? Because you are decreasing the moles in the reactions. So you have also some of these reactions that are called the hydrogenolysis, okay? The ethane by hydrogen produces methane, and the propane plus hydrogen is like a hydrocracking of light hydrocarbons present in the feedstock, and make up hydrogen is an undesirable side reactions, okay? These are extremely exothermic reactions and can develop, remember, these runaway situations. So these are our main reaction, okay? The olefins plus the hydrogen, it will produce a paraffin, okay? What kind of catalyst do we use in this section? This is a high activity nickel catalyst with this three-lobe shape. And this is operating in liquid phase. We have seen in all this unit, we are working in liquid phase. The catalyst has high activity, selectivity, and stability for hydrogenation of olefins and aromatics. We can have in situ or ex situ regeneration of the catalyst can be used to restore the activity. And the catalyst volume that we will use in the reactor is 28 cubic meters. Okay, so it is a nickel catalyst, high activity nickel catalyst. It's high activity, selectivity, and stability. And we use this volume. We can have a regeneration in situ, or we can have it outside the unit, okay, to restore the activity as the catalyst goes through the time and gets deactivated. So we have here some of the process variables. We will see the temperature, the pressure, the hydrogen makeup flow, the space velocity, and the liquid recycle flow rate. So temperature, this is a high activity catalyst, so we can operate at moderate temperatures. The high temperature favors the formation and deposit of undesirable polymers and reduces the catalyst cycle duration. As always, we have seen in this unit the same phrase. The policy is to operate at the lowest inlet temperature compatible with the sufficient catalyst activity, that is, with the required polygasoline hydrogenation rate. Because these high temperatures will favor the polymer formation on the catalyst. As the catalyst ages, the polymer deposit progressive coat the active sites and catalyst activity decreases. So how we will compensate more some of this loss of activity, we will progressively increase the reactor temperature, okay, to compensate this loss of activity. A moderate pressure level is sufficient to obtain hydrogenation of olefins and aromatics in the reactor feed. What about the hydrogen makeup flow? So small amounts of hydrogen in excess of the chemical hydrogen consumption is needed to ensure a sufficient hydrogen concentration at the reactor outlet. The flow rate should be adjusted depending upon the fresh feed rate, makeup hydrogen purity. These are the two uh, variables that you have to see to adjust the hydrogen flow rate, okay? Remember that in this case, we have a very high purity hydrogen from the PSA, so there is no problem with the hydrogen purity. And as always, related with the space velocity, typically an increase of the residence time means a higher conversion. If you have more time the feed in the reactor, we have higher conversion. This again, the formula that we have seen several times. The liquid outlet space velocity, it is always the same definition. It is the, the feed divided by the volume. And here we will see some of the operating conditions. I have said before, they are talking about 3 cases in the operating manual, okay? And these 3 cases are the normal design, that is 50% hydrogenation. You have the case 2, when you have 25% hydrogenation, and the case 3, 75% hydrogenation, okay? If you see the conditions, they are the same. The only thing that you change to go from one case to another, it is the makeup hydrogen flow rate, okay? In the case 1, where you are going to hydrogenate 50% of the olefins in the feed, you will use this at the start of run, that is 181 kilograms per hour. At the end of run, you will have more or less the same quantity. And in this case, that is case 2, that you have a lower hydrogenation, you will have lower hydrogen consumption. Okay, and in this case, that you have a higher hydrogenation, you will have a higher hydrogen makeup rate. Okay, these are more or less the operating conditions of this hydrogenation section. As you can see, you work at more or less 26 kilograms per square centimeter of pressure. These are the inlet and outlet temperature of the reactor. I have here, I think that I have the hydrogenation reactor that we have here. Okay, this is our. Let me put it smaller first. We have our reactor here. Okay, with the 28 cubic meter of catalyst. We have our product here at the bottom left from the previous section, from the oligomerization section, okay? And we mix, okay? We mix with the hydrogen, that is the blue line, it is the hydrogen, okay? We mix with the hydrogen, and of course, we mix with this recycle, okay? So here also you can see that the recycle flow rate is quite a high compared with the feed. So it is an important process variable, okay? So you have your feed that is 20 tons per hour, and you have the recycle that is about 150 tons per hour, okay? And here you have the hydrogen that, remember, for this case, that is 181. It is for the 50% hydrogenation case, for the design case, okay? You have the mixer and the appropriate also the temperature controls before you go to the reactor. So from this vessel here, from the V301, you have your products. So part will be sent to the following section, and then part you recycle back to be mixed with the feedstock. Here you can see also that you have a lot of calculators for the hydrogen also injection, and you have a lot of process control here in the unit. So these are more or less what I had prepared for today about the polynaphtha unit. As you can see, it is a important unit of the refinery. We can go to the where you have 3 sections. Remember, you have first the alkyphining section, then the oligomerization section, and the hydrogenation section. In the first section, you will remove the contaminants for the catalyst, and you will have a reactions here to selective hydrogenate the diolefins. In this case, it is the 1,3-butadiene that we have in the feedstock from the FCC unit. Here, then you will go to the oligomerization section, okay? Here you will produce your oligomers. You will separate it in the distillation, but you cannot send this stream directly to the gasoline pool because you have high content of olefins, and we have limitations in olefin content in the gasoline pool due to the gum formations. Okay, we don't want to have more than 18% volume of olefins in the gasoline that we will sell. Remember that it's a pool that we will mix with different gasoline streams. Remember that we have seen that we have reformate, we have isomerate, we have gasoline from the FCC, then we will blend it together to have our gasoline on a specification. So this oligomer from here, you will send it to this hydrogenation section to reduce the amount of olefins that we have produced in this reaction. And then we go to the stabilization column to get our product from the unit. So if you have questions about the whole presentation, please.
Thanks, Pilar. So that's it. Yeah, we finished the unit 9. Sorry. Yeah?
Yes.
Yeah. So let's see if we got a few questions from the attendees.
System as some heaters instead of fuel gas more controlled. I suppose that is also depending on the steam balance of the unit and the refinery. But usually, well, I don't know if your case, but we prefer to use steam than fire heaters, no? Even if you don't have here very high temperatures. No?
Yeah, basically, as a designers, we usually if the steam supplies
Yes.
enough heat for your process, you don't go for fired heater.
Yes.
Fired heater considered one of the most expensive
Yes.
equipment in the industry. So if you compare it to heat exchanger, it's far
From the furnace.
expensive
Yes.
than the normal heat exchanger. So that's the reason.
Yes.
ما أدري إذا
Maybe because all direction is exothermic.
لا ده السؤال ليش ما مستعملين أفران؟ ليش مبادلات؟ ما له علاقة
Yes, you always require some preheating to have the adequate temperature at the inlet of the reactors. No?
Yeah.
And you take advantage also of the outlet of the reactor to make this kind of preheating, no? of the some of the streams.
Yeah.
Yes.
Sorry, Bella, I have a question. Well, about the percentage of the olefin.
Yes.
Yes, it's undesirable, right? So why we don't reduce it at the product? If we rise the ratio of the hydrogen, so we will decrease the ratio of olefin on the product, right?
If you say, why don't we here
Why we don't reduce
in
the
the
ratio?
oligomerization section, and we avoid this hydrogenation section?
Yes, about the hydrogenation section.
Because you cannot. It will be very difficult to stop the oligomerization up to a certain value. I cannot see how. You have to convert the. You cannot say to the butenes, okay, stop now. You don't keep reacting. So so that's why they make all these olefins through this reaction, but then they have to hydrogenate part of the. So I don't see how you would.
You cannot compress all the sections in one section. So each section has got its own objective. So that's why you go step by step by doing your own conversion, and each catalyst will have its own selectivity and it has got its own mechanism and what to target and what to convert. So you cannot merge all two sections together. So
but I understand the question, because I also think,
No.
okay, you are going to olefins and then going to a step back to the to hydrogenate.
No, but why don't you do everything in the alcohol section?
So maybe it's one thing that we have to develop a new unit.
And this is a know-how. This is a know-how technology. We're not talking about I've got an idea. This is a licensed unit, so you follow the licensor.
استاذ احمد، انا سؤالي انه بالمنتج النهائي نسبة الاوليفينات اذا قلت او زادت، يعني اذا قلت انا راح استفاد اكثر.
نعم.
صح لا والله؟
اي لا هو سؤالك انه انت ليش مو الهيدروجينيشن حدثت بالاولجومرايزيشن، صح لو لا؟ لو لا مو هذا سؤالك.
لا، انا سؤالي اذا زودنا نسبة الهيدروجين بالهيدروجينيشن، هسه احنا مو عندنا 3 كيسات.
نعم.
اي فاذا مثلا اشتغل على نسبة 75% هيدروجين.
نعم.
مو 25 ولا 50، فراح تقل عندي نسبة الاوليفين اقل شيء، وتزداد عندي البارافين.
وانت راح تعتمد يعني هسه سؤالك ما له علاقه بالاولجومرايزيشن، سؤالك على الهيدروجينيشن برسنتج.
سؤالي على الهيدروجينيشن سكشن.
اي السؤال شو يقول انه شنو؟
انه ليش ما ازود نسبة البارافين واقلل نسبة الاوليفين بالمنتج؟ لانه هي كل ما تقل احسن الي.
Yeah, remember that also you have here high quantity of olefins, but smaller olefins. What you are going to do is to create bigger olefins in the reactions. So anyway, if you can use these olefins directly to the gasoline pools, no, because you have high olefin content. Because the idea is to create higher olefins, dimers, trimers in this reaction, okay?
Yeah. So one step you increase it, and the subsequent steps is to decrease it.
So one step is you increase the size of the
Yeah.
olefins.
Yes.
Always talking about olefins, and then you hydrogenate part of the olefins.
To reduce it.
Yes.
To reduce it to the required.
To reduce it.
gasoline.
Yes, you reduce this olefins content because of the specification of the gasoline pool that you.
That's understandable. But let me get his question right. I think he's asking about the ratios of hydrogen in the hydrogenation section. استاذ يعني احنا شنو بدنا نسوي هنا بالهيدروجينيشن؟ انت تقلل الاولفينز تنزلها على حساب البارافين، صح ولا لا؟
صح.
اي سؤالك شنو سؤالك؟ انا ترى لحد هسه ما فهمته.
اكثر شيء مرغوب به بالمنتج البارافين لو الاوليفين؟
لا هي مو هيك تنحسب. انت سويت بالاولجرمايزيشن زيدت الاولفينات، انت تريد اولفينات، بس الاولفينات بيها مشكله لحد هسه متفقين مو؟
سوي قام اوكي متفقين.
اي بس اسمح لي الاولفينات انت عندك لها نسبه معينه لازم موجوده بالغازولين بول اللي هو يجيها من عده سورسز. الغازولين بول فاهمني؟
تمام.
يجيك يجيك ايزومريت، يجيك ريفورميت، صح؟ ويجيك هذا البوليغازولين. بس انت عندك نسبه معينه من الاولفينز ما ممكن تتجاوزها، ما مسموح بها لانه تصير اوف سبيسيفيكيشن من المنتج. هاي شلون تخلص منها وتسيطر عليها؟ بعمليه الهيدروجينيشن. تمام
يعني اكو ليميت بالبول يعني
بالضبط. اكو 25% واكو 75% هيدروجين. حسب المطلوب، حسب المعلومه الموجوده عندك اياها بالغازولين بول، بالبلند مالتك، بالخلط مال الغازولين.
تمام استاذ، شكرا. Thank you Bella. I'm
You're
sorry
welcome.
for my question. Maybe
No, please ask. I love when you ask. So
maybe I am asking too much questions.
No, please feel free to ask whenever you want.
Thank you.
براحتك. احنا نريدكم تسالون. احنا نريدكم تسالون استاذ امير، الله يبارك فيك.
We've got another question, slide 31.
Yes. 31.
Why the outlet temperature of a reactor is not the inlet temperature for the next one?
For the next one,
31.
Have the remember that we have intercoolers after each reactor. So if we have 145 here, we will cool until 120 to enter to the second reactor, and so on. Okay.
Yeah, that is cool.
We have intercooling in between in each reactor.
Thanks.
واضح ست دعاء؟ واضح الجواب؟
نعم استاذ
واضح؟
نعم استاذ واضح.
Okay. That's clear. Bila. Thank you.
Okay. So
there is another question, Shabab.
Yes.
Chatting.
What's that? So do you need to decreasing the temperature between the reactors? Yes, you decrease the temperature.
Yes. I don't know. Yes, we have in the here. Remember that we have these intercoolers.
Yeah.
We have to cool the outlet from the first to reach the temperature, adequate temperature for the second, and also for this.
Okay, I think that's clear. Okay, any more questions? I don't see more questions so far. Okay.
Maybe Ahmed, Mr. Ahmed, maybe the reason for the cooling. The question is
why we cool in between.
Why we cool? Yes, maybe we control the organization ratio.
No, you've got every reactor, as everyone knows, that you have a optimum temperature, optimum pressure.
Yeah.
So you try to meet it. Otherwise, you have accumulated heat, or you're not going to.
Sometimes we need to preheat. Sometimes we need to cool.
Conversion. You're not going to achieve your conversion. Yes. So if your conversion is
okay, maybe
If you don't cool, it becomes 70%, and then you maybe produce.
Yes, maybe it's
And so on.
increase the amount of organization.
Yeah.
اوكي. واضح سيد دعاء؟ واضح الجواب؟
نعم أستاذ، كلش واضح.
اوكي.
تسلم أستاذ.
هو أستاذ ضرغام أصور همين هذا السؤال. اوكي، أستاذ رعد تفضل، أو رائد.
السلام عليكم، شلونكم أستاذنا؟
السلام ورحمة الله. ترى رعد لو رائد؟ أنا ترى الاسم بالإنجليزي دا أشوفه.
إيه هو رعد أستاذ.
رعد، نعم.
بما أن أستاذ عدي هم موجود، شلونك أستاذنا؟
حبيبي أستاذ، هلا بيك.
الله يحفظك. مثل ما عرفنا أستاذ، ذن 3 وحدات